Good morning. Today we're going to talk about free body diagrams. So free body diagrams are essentially a set of tools, procedures used to isolate a part within a bigger system. And by studying that part only, you'll be able to see how it interacts with its environment and be able to do engineering calculations based on that. Let me start by showing you a little example of a free body diagram. Imagine we have a box, side view of a box right here, and we place the ball inside that box, and the ball rests in that corner right here. And then you place another ball, slightly smaller, and it will kind of wedge itself right here. So it will be touching this side right here, touching this side right here, like this. Okay? So we can call this object 1, we can call this object 2, and the box itself, we could call this object 3. So granted, this is a two-dimensional drawing, but we are starting with fairly easy stuff. We'll move on to more difficult things later. Okay? So we can do several free body diagrams here. Again, a free body diagram is when we choose one of the parts in the system. So we could do a free body diagram for part 1, one for part 2, or one for part 3. Okay? For part 3, it's not that interesting, but we're going to do it for part 1 first. Okay, so let's do the free body diagram for 1. So basically what I'm going to do is I'm going to think of it as this part right here. I'm going to take it outside of this box, but for this not to move right here, it is after all in static equilibrium. It's not moving because it has a lot of forces applied to it. So since it is tangential right here to the side of it, at the point of tangency right here, I'm going to have a force going in that direction. Okay. We have another point of tangency right here, so I'm going to have a force going in this direction right here. And over there, I have another point of tangency, and the force is going to be in a normal direction. Normal means perpendicular to the tangent. Okay? Or if you prefer, it's also going to be in a direction connecting the two centers right here. So it's going to be approximately in this direction right here. Right? It's going to go through the center right here. So this here is applying a force in that direction to it, because without it the ball will move in that way, so the force is that way, right? Right here, without this surface, the ball will fall, that means the force goes up, okay? And right here, without this ball, this number 2 ball will go in that direction, right? So that means that the force goes in that direction right here. Now, I have a problem with that. It seemed to me that it's really not making sense. Because this force right here, is it really correct? If we think about this force right here is the force of this pushing on this. This force right here is the force of this pushing on this. So the force right here should be the force of this pushing on this. So don't you think it should be in the other direction? Yes. So what we're going to have right here is, instead of having this right here, we're going to have this right here. Now, this is still not a free body diagram. The reason being that we want all the forces to start in the same place. So what we're going to do here is we're going to draw a little centroid symbol. So just like this. And this here is going to be representing the centroid of this part right here. And then we're going to, from the centroid, draw all forces. So we're going to have this one, we're going to have this one, and we're going to have this one right here. Okay? So that's a free body diagram, but we need to label those vectors. Those are vector forces, right? We need to label those in order to then use them. Okay? So we can use different kind of convention, but I'm going to call this the force of 3 onto 1. F3, 1. This I'm going to call it the force of 3 onto 1 as well. And here I'm going to call it the force of 2 onto 1, like this. So this is a little weird because we have the same nomenclature essentially for two different forces. So since this one will be in a vertical direction, we can associate that to a y, and this is in the x direction, so we're going to call it x. Here it has a component in x and y direction, so we're going to leave it like that. Okay? Of course, we're going to assume for all problems that this is the x direction and this is the y direction. We're going to have to quantify those vectors, those components, therefore we need a direction to do so. Okay. Real fast, let's do the same thing for the second, in this case, circle. I'm going to start directly with my centroid, and Newton's third law says that to every action there is an equal and opposite reaction. That means that the force of 2 onto 1 will be, for the 2, the force of 1 onto 2. Okay. So those two vectors, the vector F21 and the vector F12, have the same direction, offset by 180-degree angle, and the same length or magnitude. Okay. So that would be right here, and then we have a force over there as well. So the force from 3 onto 2. And it is in x direction. Okay. Do we have a force in the y direction? Not really. Alright, are we done with this? Yes, no? Well, there's one more little thing right here. Those two parts are made out of matter. That means we have the weight of the part as well. Okay, so right here we're going to have the weight of it. I'm going to call it W. I'm going to represent it right here. And I'm going to have this. Okay, maybe I can call it W1 and here W2. Okay. If you want to relate that to a typical physics example, you could have the example of an inclined plane that forms an angle alpha with the horizontal like this, and then you could have a box on top, and the box maybe has a mass m, and maybe we have a static coefficient of friction mu right there, and the box is just sitting there. What would be the free body diagram for that? Well, we would have the mass acting with gravity creating the weight right here. We would have the normal force right here, okay, perpendicular to the plane, and we would have a little bit of a friction force right here. So a free body diagram in that case would become something like the weight, the normal force right here, and we would have a force of friction right here that forms an angle alpha with that. Okay? Um, we're not talking yet about x-axis, y-axis here because we have different options. The free body diagram though exists regardless of those choices involving future components or vectors. I hope it was helpful.